There was a moment when the universe became transparent. This happened roughly 380,000 years after the universe began. The change was gradual. Electrons settled into orbit around atomic nuclei. Hydrogen atoms formed. Helium atoms formed. Light no longer scattered constantly off free electrons. Space became clear. This moment is called recombination. The term is used by scientists even though it describes a first-time combination rather than a recombination. The naming persists. The universe transitioned from opaque to transparent. Light could travel without constant interruption. This marks the end of one era and the beginning of another. The light released during recombination still exists. It has been traveling through space ever since. We call it the cosmic microwave background. The expansion of space has stretched this light over billions of years. What was once visible light is now microwave radiation. The temperature of this radiation today is approximately 2.7 degrees above absolute zero. It comes from all directions. It fills all of space evenly. This story begins after that light was released, after the universe became transparent, after recombination had occurred. This story is about what followed. The universe was transparent, but there were no stars yet. There were no galaxies. There was matter, but that matter did not produce light. This story is about that time, about the darkness that followed transparency. The period is called the Cosmic Dark Ages. It lasted for hundreds of millions of years. During this time, the universe expanded. It cooled. Matter drifted through space. No new light was being created. The only light was the cosmic microwave background, growing fainter and more redshifted as space continued to expand. The universe was dark. It remained dark for a very long time. This darkness was not an absence, it was a presence. Space existed. Matter existed. Time passed. The universe had become transparent, but transparency without sources of light meant only that the darkness was clear rather than obscured. You could see through space if there had been eyes to see. But there was nothing to see. No stars, no glowing gas, just darkness, extending in all directions, uniform and complete. The cosmic microwave background provided the only electromagnetic radiation present. This radiation was uniform across the sky. Its temperature was dropping as space expanded. In the early Dark Ages, shortly after recombination, the temperature of this background radiation was still a few thousand degrees. Over time, it cooled. After 1 million years, it had cooled to a few dozen degrees. After 10 million years, it was colder still. The cooling was continuous and steady. Space itself continued to expand during this period. The expansion had no center. There was no edge. Every point in space was moving away from every other point. This expansion was smooth and uniform. The rate of expansion was gradually slowing due to the gravitational pull of all the matter in the universe. But the slowing was gradual. The expansion continued without pause. For a very long time, nothing in the universe was illuminated. There is nothing you need to do. Just listen. Neutral hydrogen filled the universe during this time. Each hydrogen atom consisted of one proton and one electron. The proton formed the nucleus. The electron orbited that nucleus. The electromagnetic force held them together. These atoms were stable. They were electrically neutral. They did not emit light under the conditions that existed then. Helium was also present. Helium made up approximately 25% of the matter by mass. Each helium atom had 2 protons, 2 neutrons, and 2 electrons. Helium was also stable and neutral. There were trace amounts of lithium as well. Lithium has 3 protons. These 3 elements, hydrogen, helium, and lithium, were the only elements present. No heavier elements existed yet. The gas was very diffuse. On average, there might have been a few hundred atoms in a volume the size of a sugar cube. In some regions, there were fewer. In other regions, slightly more. The variations were small. The universe was relatively uniform at this stage. The gas filled space evenly, thinning gradually as space expanded. Temperature declined steadily. When recombination occurred, the temperature of the gas was approximately 3,000 degrees. As the universe expanded, that temperature fell. There was no external source of heat. The thermal energy from earlier times simply spread across a larger and larger volume. After 1 million years, the temperature had dropped to a few dozen degrees above absolute zero. After 10 million years, it was colder still. The cooling continued without pause. The gas drifted through space. Individual atoms moved according to their thermal motion. They traveled in straight lines until they encountered another atom, which happened rarely given the low density. Most atoms were isolated, separated from their neighbors by distances far larger than the atoms themselves. Collisions were infrequent. When atoms did collide, they bounced off one another elastically, changing direction but losing no energy. The motion was random. There was no preferred direction, no flow, just individual atoms moving through the void. Space continued to expand. This expansion was not an explosion. Nothing was moving outward into a void. Space itself was growing. The distance between any 2 points increased gradually over time. This stretching was uniform. Every region of space expanded at the same rate. The hydrogen atoms moved apart from one another, not because they were traveling through space, but because the space between them was increasing. An atom at rest relative to the expanding space would still find itself farther from its neighbors with each passing moment. The universe had no center. There was no edge. Every location was equivalent to every other location on large scales. An observer at any point would have seen the same thing in all directions. Darkness, with the faint glow of the cosmic microwave background growing steadily dimmer and cooler. Time passed. Millions of years accumulated. The conditions changed slowly, smoothly, without sudden transitions. The temperature dropped. The density decreased. The cosmic microwave background redshifted further into longer wavelengths. The hydrogen remained neutral, dark, and transparent. Gravity operated throughout this period. Gravity is always present wherever there is mass. The hydrogen atoms had mass. Dark matter had mass. Gravity pulled every piece of matter toward every other piece of matter. The force was weak over large distances, but it never stopped acting. It operated continuously, without variation, pulling matter together at a rate determined by the amount of mass present and the distances involved. The distribution of matter contained small irregularities. Some regions had slightly more hydrogen than average. Other regions had slightly less. These differences were minor, typically 1 part in 100,000. A region with 100,000 atoms might have 100,001, while another region might have 99,999. The variations were subtle, but they were real. They originated during earlier epochs and persisted as space expanded. Gravity amplified these differences over time. In a region with slightly more matter, the gravitational pull was slightly stronger. This stronger pull attracted more matter from the surrounding space. The accumulation happened slowly. Over millions of years, regions that started slightly denser became incrementally denser. Regions that started slightly less dense became incrementally emptier. The process was gradual and continuous. There were no sudden collapses, no rapid changes, just steady, patient accumulation of matter in the denser regions, and steady depletion of matter in the less dense regions. Dark matter participated in this process. Dark matter does not interact with light. It does not emit radiation. It does not absorb radiation. It interacts only through gravity. During the cosmic dark ages, dark matter was collapsing into concentrations under its own gravitational attraction. These concentrations are called dark matter halos. They formed invisibly, detectable only through their gravitational effects. The dark matter fell inward toward the densest points, accumulating slowly, building up structures that would later serve as the gravitational scaffolding for galaxies. The hydrogen gas responded to the gravity of these dark matter halos. Where dark matter concentrated, hydrogen began to accumulate as well. The gas fell slowly inward toward the densest regions. This infall was gentle, occurring over timescales of millions of years. The hydrogen added its own gravitational contribution to the growing structures, reinforcing the process. The gas settled into the potential wells created by the dark matter, following the gravitational gradients, moving inward at speeds of perhaps a few kilometers per second, which over millions of years could transport gas across vast distances. Nothing about this process was rapid. The universe was patient. Time was abundant. The gravitational collapse proceeded at its own pace, governed by the density of matter and the expansion of space. In regions where matter was denser, collapse proceeded slightly faster. In regions where matter was more diffuse, collapse proceeded more slowly. Everywhere, the process continued, quiet and persistent. The structures grew slowly. The density increased incrementally. The universe developed texture, though that texture remained invisible in the darkness. The density remained low even as matter began to concentrate. In the regions where hydrogen was accumulating most rapidly, the density might have reached a few thousand atoms per cubic centimeter after tens of millions of years. This was still far more diffuse than any vacuum we can create artificially. The gas was nearly transparent. It was nearly massless. It drifted slowly inward, following the gravitational gradients established by the dark matter, settling gradually into the structures that would, much later, become galaxies. The hydrogen remained neutral throughout this period. Each atom consisted of a proton and an electron bound together. The electron occupied its lowest energy state. In this configuration, the atom was stable. It did not emit light. It simply existed, dark and quiet, drifting through space. Neutral hydrogen can emit a particular wavelength of radiation, 21 centimeters, when the electron's spin flips relative to the proton. This happens very rarely for any individual atom, perhaps once every 10 million years. With countless atoms present, this emission occurred somewhere continuously, but the total radiation produced was faint. It added to the background, nothing more. The universe contained the cooling microwave background and this faint hydrogen emission. No other sources of radiation existed. The spectrum was simple. The intensity was low. Space was dark across nearly all wavelengths. Radio, microwave, infrared, visible, ultraviolet, X-ray. All were essentially absent except for the uniform primordial glow that filled space. The hydrogen drifted. It moved under gravity's influence. It moved with the expansion of space. It moved with residual thermal motion from earlier times. These motions were slow. An atom might travel a few kilometers per second relative to the surrounding gas. Over millions of years, this could carry it across thousands of light years. But space was uniform. One region resembled another. The hydrogen simply drifted, part of the larger flow responding to gravity and expansion. Each atom traveled alone most of the time. The distances between atoms were vast compared to the size of the atoms themselves. An atom might drift for years without encountering another atom. When encounters did happen, they were brief. The atoms passed by one another or collided gently, exchanging momentum, then continued on their separate paths. There was no clustering on these small scales, no gathering of atoms into groups, just individual particles moving through the void. The temperature of the hydrogen continued declining. Shortly after recombination, the gas temperature matched the radiation temperature. Both were approximately 3,000 degrees. As space expanded, both cooled. The cooling was linked at first. The hydrogen and radiation exchanged energy through occasional interactions. The temperatures stayed matched. Over time, this connection weakened. The density of matter decreased as space expanded. Interactions became less frequent. The gas and radiation began cooling at slightly different rates. The gas cooled more slowly in some circumstances. The details involved the expansion rate and how often particles interacted. The overall effect was a gradual separation of matter temperature from radiation temperature. The two systems began following their own paths. The hydrogen temperature dropped steadily. After 1,000,000 years, it was perhaps a few hundred degrees. After 10 million years, cooler still. The exact values depended on conditions in different regions, but the trend was consistent everywhere. The gas grew colder. The decline continued without interruption. There was nothing to reverse the cooling. No energy sources existed to heat the gas back up. The thermal energy simply diluted across the expanding volume of space. Helium drifted through space alongside the hydrogen. Helium atoms have 2 electrons in a stable configuration. They do not react with other elements under ordinary conditions. They do not form molecules. Each helium atom existed independently, contributing its mass to gravity, but otherwise inactive. The proportion remained constant. Roughly 1 helium atom for every 12 hydrogen atoms. By mass, helium made up about 1/4 of the total. This ratio had been set during the first few minutes of the universe. It did not change during the Dark Ages. No processes existed that could alter it. The atoms simply persisted as the universe expanded around them. Lithium was also present in very small amounts. Lithium has 3 protons. It behaved much like hydrogen and helium during this time. It drifted. It responded to gravity. Its abundance was roughly 1 atom for every 10 billion hydrogen atoms. Rare but present. These 3 elements represented the complete chemical inventory. No carbon, no oxygen, no iron. Nothing heavier than lithium existed yet. The universe was chemically simple. The complexity that would later emerge had not yet begun. Only the lightest elements were present, formed in the immediate aftermath of the universe's beginning. The gas had no structure on small scales. Individual atoms were isolated. They did not bond together. Molecular hydrogen can form under certain conditions, but those conditions did not generally exist yet. The density was too low. The temperature was not right for molecule formation. Most hydrogen remained atomic, one atom at a time, separate and alone. The atoms moved through space without pattern. There was no organization to their motion on small scales. Each atom followed its own trajectory, influenced by its own velocity and the gravitational field of the surrounding matter. The trajectories were essentially random when viewed individually. Only when considering billions of atoms together did patterns emerge, as the collective motion responded to the large-scale gravitational field. On large scales, structure was emerging slowly. The density variations present at recombination were growing. Regions that started slightly denser were becoming more dense. After 10 million years, the variations had grown somewhat. After 50 million years, they had grown more. The growth was steady. The doubling time was long. Millions of years passed between noticeable changes in density contrast. The less dense regions were also evolving. Where matter was below average density, the deficit grew. These regions expanded faster than the average. Matter flowed out of them, drawn by the gravity of denser regions. Over time, these became voids. They grew larger and emptier. The universe developed a pattern of denser regions separated by voids, a structure that would eventually span immense distances. The flow of matter was gentle. Gas did not rush from voids into dense regions. It drifted slowly, following the gravitational gradients. The velocities were measured in kilometers per second at most. Over millions of years, these modest velocities could transport gas across vast distances, but at any given moment, the motion was imperceptible. The universe was reshaping itself gradually, without haste. The cosmic microwave background continued cooling. Its temperature dropped in direct proportion to the expansion. When the universe doubled in size, the temperature dropped by half. The wavelength of the photons stretched with the expansion. Longer wavelengths meant lower temperatures. The cooling continued steadily. After 1 million years, the background temperature was approximately 300 degrees above absolute zero. After 10 million years, approximately 30 degrees. After 100 million years, approximately 3 degrees. The exact values depended on the expansion rate, which itself depended on the total density of matter and energy. The general trend was consistent. The temperature fell. The universe grew colder. The radiation filled all of space uniformly. It came from every direction equally. There were no hot spots or cold spots on large scales, only tiny variations that reflected the density variations in the matter. These variations were small, 1 part in 100,000. The background was remarkably smooth and uniform. The hydrogen gas cooled as well. The gas had pressure. It could compress and expand. When gas fell into a denser region under gravity, it compressed slightly and warmed. When gas expanded in a less dense region, it cooled. These local variations were small compared to the overall cooling, but they existed. The gas was not uniform in temperature everywhere. There were no heat sources, no stars, no glowing disks, no explosions. The only energy came from gravitational potential converting to motion as gas fell inward toward denser regions. This heating was minimal. The velocities were small. The compression was gentle. The temperature increases were modest. The universe was reaching its coldest state. Before stars formed, the gas temperature would drop to perhaps 10 or 20 degrees above absolute zero in some regions. This was the coldest ordinary matter in the universe has ever been. Once stars began forming, they would heat their surroundings. But during the Dark Ages, the universe cooled without interruption. The cold was not threatening. It simply existed as a condition of the universe at that time. The gas had no awareness of its temperature. The atoms continued their motion, slowed by the declining thermal energy, but still moving. Even at 10 degrees above absolute zero, atoms retain some motion. They vibrate. They drift. They do not stop completely. The cold meant only that the average kinetic energy was low. Dark matter continued collapsing. Dark matter does not resist compression the way ordinary matter does. It simply moves under gravity's influence. When dark matter fell toward a denser region, it accelerated inward. When it reached the center, it passed through and emerged on the other side, then fell back. Over time, the orbits crossed and recrossed. The dark matter settled into roughly spherical configurations called halos. The halos grew over time. Small halos formed first. These merged with other small halos to form larger ones. The merging was ongoing. At any time, some halos were combining while others remained separate. The largest halos contained the most mass. Their gravitational pull was strongest. Over tens of millions of years, a distribution of halo masses developed. The hydrogen followed the dark matter. Where dark matter formed halos, hydrogen accumulated. The gas fell into the gravitational wells created by the dark matter. It settled toward the halo centers, increasing the density there. The process was slow. The gas did not fall straight inward. It had angular momentum from the larger scale motion of the region. The gas settled into rotating distributions within the halos, flattening slightly along the rotation axis. As the universe continued its slow and steady expansion, subtle changes began to take hold within its calm simplicity. Space kept widening and cooling continued, but now the passage of time began to leave gentle traces. Matter, still simple and sparse, had been drifting quietly for a very long while. In that quiet drift, small differences began to matter in ways they had not before. Atoms moved through space almost alone, separated by immense distances that were still growing. Yet they were never completely isolated. Gravity, though extremely gentle, was always present. It did not rush or pull suddenly. It worked slowly and patiently, influencing matter across vast spans of time. Where matter happened to be just slightly more concentrated, gravity's influence was just a little stronger, almost unnoticeable in any single moment. These early differences were not dramatic. They were not sharp contrasts or sudden clumps. They were gentle variations, barely noticeable at first and easy to overlook. But over long periods, gravity allowed these variations to persist rather than fade away. Expansion continued to stretch space, but gravity quietly resisted that stretching in certain regions, slowing it just enough to leave a lasting effect. Matter began to respond to these subtle imbalances. atoms drifted toward regions where density was slightly higher, not because they were guided or directed, but because gravity made those paths marginally easier to follow. This movement was slow and unhurried. Nothing collapsed, nothing rushed together. Matter simply lingered a little longer in some places than in others, carried by time rather than force. As time passed, these lingering effects accumulated. Regions with slightly more matter became just a bit denser. Regions with slightly less matter became just a bit emptier. The differences remained small, but they no longer disappeared completely. The universe had entered a phase where change came not from intensity or violence, but from patience and persistence working quietly together. Throughout this process, the universe remained calm and transparent. Light continued to travel freely, stretched by expansion and softened by time. Matter remained simple, mostly hydrogen and helium atoms drifting calmly through space. There were still no stars, no galaxies, and no concentrated sources of light to interrupt the uniform stillness. Gravity's role during this era was subtle but essential. It did not overpower expansion or reverse it. Instead, it worked alongside expansion, allowing slight unevenness to endure. Where expansion tried to separate everything evenly, gravity permitted small preferences to form and remain over long stretches of time, shaping motion gently rather than decisively. From a broad perspective, the universe still appeared smooth and uniform. The changes were local, quiet, and gradual. They unfolded over millions of years without producing sudden transitions or visible landmarks. Nothing announced that matter was beginning to take shape. Nothing marked the moment. Time continued to pass without ceremony. The universe did not signal that organization had begun. It simply allowed physical laws to operate consistently, everywhere at once, guiding matter along the easiest available paths while maintaining its overall calm. Matter was no longer drifting entirely at random. It was beginning to respond to its surroundings in a lasting way, not through collapse or structure yet, but through gentle direction. The cosmos remained vast, transparent, and unhurried, carrying matter forward as the earliest hints of structure quietly took root in the background of deep time. Time continued to pass, and the quiet shaping of matter became slightly more noticeable, though still gentle and unhurried. Expansion remained steady, and cooling continued as it had for a long time. But gravity's patient influence had now been at work long enough for its effects to deepen. Matter was no longer drifting entirely without consequence. Small differences that had once seemed insignificant were beginning to hold their place. Atoms continued to move through space at great distances from one another. Most of the universe was still empty by any familiar measure, with vast regions containing almost nothing at all. Yet in certain areas, matter lingered just a little longer than elsewhere. These regions were not compact or dense. They were simply places where atoms passed through more slowly, guided by faint gravitational preference rather than chance alone. Gravity did not pull matter inwards suddenly or dramatically. It acted quietly, altering motion only slightly. Where density was just a bit higher, gravity bent paths almost imperceptibly. Over long spans of time, these small adjustments accumulated. Atoms that passed through these regions were more likely to drift back again, returning slowly instead of moving on forever. Expansion continued to stretch space, gently encouraging separation everywhere. Gravity responded by slowing that separation in select areas, not stopping it, but easing it. The result was balance rather than struggle. Neither force dominated. Instead, expansion and gravity shaped motion together, patiently and without urgency. Matter responded slowly to this balance. Nothing collapsed, nothing ignited. There were still no stars, no galaxies, and no concentrated sources of light. Yet the universe was no longer perfectly uniform. Subtle patterns were beginning to appear, written not in structure, but in motion and tendency. Light continued to travel freely through space, stretched by expansion and softened further with time. It passed through these emerging regions without disturbance, carrying no visible sign of change. From any broad perspective, the universe still appeared smooth and calm, much as it had before. As millions of years passed, gravity's influence became more consistent in these favored regions. Matter did not gather quickly, but it gathered reliably. Each gentle pass made future passes more likely. Over time, this quiet repetition mattered. Persistence slowly replaced randomness. Cooling supported this process. With lower energy, matter was less easily scattered by motion. Atoms moved more predictably, responding gently to gravitational influence rather than drifting freely in all directions. The universe remained calm, but it was no longer indifferent to where matter traveled. There were no boundaries marking this shift. The universe did not announce a new phase or signal that organization had begun. It simply allowed gravity more time to shape motion. Physical laws continued to operate consistently, everywhere at once, without urgency or intent. These regions were still far from becoming structures. They were only beginnings, faint tendencies rather than formations. But those tendencies mattered. Given enough time, they would lead somewhere new. For now, they remained subtle and quiet. The universe stayed vast, transparent, and unhurried. Matter and light shared space calmly. Expansion continued. Cooling continued. And within that calm, gravity continued its slow work, guiding matter along paths that would, much later, give rise to clearer and more recognizable forms. The gentle shaping of matter progressed without urgency. Expansion remained steady, and cooling continued at its familiar pace. But gravity's quiet influence had now been acting long enough to deepen the patterns it had begun. Matter was still sparse and widely separated, yet it no longer moved without context. Its paths were becoming slightly more predictable, shaped by subtle preferences rather than chance alone. Atoms drifted through space in slow, patient motion. Vast regions remained nearly empty, while other areas held just a little more matter than their surroundings. These differences were still small and easy to overlook, but they endured. Gravity did not force matter together. It simply allowed certain regions to remain welcoming, encouraging atoms to pass through again and again over long stretches of time. Each return mattered. Atoms that lingered were more likely to encounter others following similar paths, not in sudden meetings, but in repeated proximity. Over time, this quiet repetition increased the chance that matter would remain nearby rather than disperse completely. The universe was still calm, but it was becoming quietly selective. Expansion continued to widen space everywhere, gently pulling matter apart. Gravity answered not by reversing that motion, but by softening it locally. Where matter was slightly more common, separation slowed just enough to make a difference. Neither process dominated. Expansion and gravity remained balanced, shaping motion together across immense spans of time. Cooling supported this balance. With less energy driving motion, atoms moved more smoothly and predictably. Their paths were less chaotic, more responsive to gentle influence. Matter did not rush. It drifted, paused, and drifted again, guided by conditions that favored patience over speed. Light continued to pass freely through the universe, stretched by expansion and softened further with time. It revealed nothing dramatic. To any broad view, the cosmos still appeared uniform and quiet. The changes taking place were subtle, visible only through their long-term effects rather than immediate transformation. As millions of years passed, these favored regions became slightly more distinct. Not dense, not bright, but quietly persistent. Matter did not gather into objects, but it began to show preference for certain paths and locations. The universe was still far from forming stars or galaxies, yet it was no longer entirely without direction. There were no signals announcing this progression. No boundaries marked the shift from drifting to gathering. Physical laws continued to operate evenly, everywhere at once, without intention or awareness. The universe simply allowed time to do its work. From within this vast calm, matter began to carry a memory of where it had been. Paths repeated, regions grew familiar. What had once been uniform randomness slowly gave way to gentle pattern. Not structure yet, but the quiet groundwork for it. The universe remained transparent and unhurried. Matter and light shared space without disturbance. Expansion continued. Cooling continued. Gravity shaped motion in the background, patiently and consistently. By the end of this phase, matter was no longer only drifting through space. It was beginning to linger, to return, and to respond in lasting ways. The changes were still faint and slow, but they mattered. Given enough time, they would lead to clearer forms and deeper complexity. For now, the cosmos rested in motion, guided not by events, but by continuity. Expansion, cooling, and gravity worked together quietly, carrying matter forward through deep time as the earliest foundations of structure settled gently into place. Gravity operated continuously throughout this period. It acted on every particle of matter, pulling them toward one another according to their masses and distances. The force was weak at large separations, but never absent. Even atoms separated by millions of light years exerted some gravitational influence on each other, infinitesimal but real. The cumulative effect of gravity over time was substantial. Individual atoms moved slowly, but millions of years allowed those slow movements to carry atoms across vast distances. An atom drifting at a few kilometers per second would travel several thousand light years over 10 million years. This was enough to allow significant redistribution of matter across space. The overdense regions continued attracting matter from their surroundings. Gas flowed inward gradually, drawn by the gravitational pull of the concentrated matter. The flow was smooth and continuous. There were no sudden inflows or dramatic collapses at this stage. The gas simply drifted inward, following the gravitational gradient, accumulating slowly in the densest regions. The gravitational field itself was smooth on large scales. The overdensities were gentle enhancements, not sharp peaks. A region that was 10% denser than average might span thousands of light years. The gravitational pull increased gradually as one moved toward the center of such a region. There were no steep gradients, no sudden changes in the strength of gravity. Dark matter dominated the gravitational field. Dark matter made up roughly 5 times as much mass as ordinary matter. The dark matter distribution determined where the gravitational wells formed. The dark matter halos created the potential wells, and the ordinary matter fell into those wells. The dark matter was the framework, the scaffold on which structure formed. The dark matter halos themselves were not static. They grew through accretion of additional dark matter. Small halos merged to form larger ones. The merging process was gradual. 2 halos would approach each other over millions of years, their relative velocity determined by their mutual gravitational attraction. As they drew closer, they began to orbit each other. Eventually, they merged into a single, larger halo. The merger process was gentle for dark matter. Dark matter particles do not collide in the way ordinary matter does. They pass through each other, interacting only through gravity. When 2 halos merged, the dark matter particles from both halos simply intermixed, their orbits crossing and recrossing until they settled into a new equilibrium configuration. The process took millions of years to complete. The hydrogen responded differently to mergers. When gas from 2 regions came together, the atoms could collide. The collisions were still rare given the low density, but they happened more frequently than in the surrounding space. The collisions transferred momentum and energy. The gas could shock and heat slightly during mergers, though the heating remained modest given the low velocities involved. The distribution of matter was developing a pattern. The densest regions became nodes in a larger network. Between these nodes, matter was distributed in filaments and sheets. The filaments connected the nodes, channels along which matter flowed. The sheets were broader structures, walls of slightly enhanced density separating the larger voids. This structure is sometimes called the cosmic web. It emerged naturally from the gravitational amplification of the initial density fluctuations. Where matter was slightly overdense in a linear pattern, gravity caused that pattern to collapse, preferentially along certain directions, forming filaments. Where matter was overdense in a sheet-like pattern, it collapsed into walls. Where matter was overdense in all directions, it formed nodes. The structure was not yet prominent. The density contrasts were still small. A filament might be only a few % denser than the surrounding space. A wall might be similar. The voids were only slightly less dense than average, but the pattern was there, and it was growing. Over time, the contrast would increase. The filaments would become denser. The voids would become emptier. The structure would become more pronounced. The hydrogen flowed along the filaments toward the nodes. The filaments acted as channels, guiding matter from larger volumes of space into the densest regions. Gas in a filament experienced gravitational pull from the nodes at either end. It accelerated slowly toward those nodes, flowing along the filament at velocities of perhaps 10 to 20 kilometers per second. The flow was laminar. The gas did not tumble or swirl in complex patterns. It flowed smoothly along the gravitational gradients. The velocities were low enough and the density sparse enough that turbulence did not develop. The motion was orderly, organized by gravity, following the simplest paths through the gravitational field. The voids continued expanding. Where matter was less dense than average, the local expansion rate was higher. The matter in these regions felt less gravitational attraction, both from within the void and from surrounding regions. The void expanded faster than the universe as a whole. Matter near the edges of voids felt gravitational pull from the denser regions outside, drawing the matter outward, away from the void center. Over time, the voids grew larger and emptier. After 50 million years, a region that started 10% less dense than average might be 30% less dense. After 100 million years, it might be 50% less dense. The depletion was gradual but cumulative. Matter steadily left these regions, flowing toward the overdense areas, leaving the voids more and more empty. The universe was organizing itself. The initial tiny variations in density were being amplified into a structured pattern of overdense nodes connected by filaments, surrounded by expanding voids. The process was slow but inexorable, driven by gravity, operating everywhere throughout space simultaneously. The temperature structure of the universe was becoming more complex. In the voids, the gas continued cooling unimpeded. The density was low. The expansion was faster than average. The temperature dropped smoothly following the expansion, reaching perhaps 10 to 15 degrees above absolute zero in the deepest voids. In the overdense regions, the temperature evolution was different. The gas falling into these regions compressed slightly. Compression heats gas. The heating was modest, raising the temperature by perhaps a few degrees to a few tens of degrees, depending on how much the gas compressed. The gas in overdense regions remained cold by most standards, but it was warmer than the gas in the voids. The temperature differences were small in absolute terms. The difference between 10 degrees and 30 degrees might seem negligible, but in the context of the cosmic dark ages, these were significant variations. The universe was no longer uniform in temperature. It had developed structure in its thermal properties, just as it had in its density. The pressure of the gas responded to these temperature changes. Pressure in a gas depends on both temperature and density. In the overdense regions, both temperature and density were higher, so the pressure was significantly higher than in the voids. This pressure difference had consequences. Pressure can resist gravitational collapse. Pressure can support gas against further compression. At this stage, the pressure was still very low in absolute terms. The gas was so diffuse that even in the overdense regions, the pressure was negligible by familiar standards. The pressure was not yet strong enough to significantly resist gravitational collapse. The gas continued falling into the halos, compressing, slowly increasing in density despite the modest pressure support. The gas settled into a state approaching equilibrium in some regions. Equilibrium occurs when the inward pull of gravity is balanced by the outward push of pressure. In the centers of the densest halos, the gas was beginning to approach this balance. The density had increased enough that the pressure was becoming significant. The compression slowed. The gas settled into a more stable configuration. This equilibrium was not static. The halos continued growing as more matter fell in. The gravitational field strengthened as the mass increased. The gas responded by compressing further, raising the pressure until a new balance was reached. The process was dynamic, with the equilibrium point shifting gradually as the halo evolved. The gas in equilibrium was still cold. The temperatures were still measured in tens of degrees, not hundreds or thousands. The pressure was still low. density was higher than in the surrounding space, but still very diffuse by familiar standards. A cubic centimeter of gas in a halo center might contain a few thousand atoms. This was dense by the standards of the cosmic dark ages, but it was still an excellent vacuum by terrestrial standards. The hydrogen remained neutral throughout these processes. The temperatures were far too low to ionize hydrogen. Ionization requires temperatures of thousands of degrees or the presence of high-energy photons. Neither condition existed. The electrons remained bound to their protons. The gas stayed dark. It did not emit light. It simply existed, cold and neutral, slowly gathering in the gravitational wells created by the dark matter. The universe continued in this state for tens of millions of years. Structure grew slowly. Halos merged gradually. Gas accumulated in the densest regions. The temperature declined in the voids and stabilized in the halos. Time passed. The universe aged. The conditions evolved smoothly, without sudden changes, following the patient logic of gravity and expansion. The dark matter halos were invisible. They contained no ordinary matter at first, only dark matter particles moving through the gravitational field they collectively created. The halos had mass, they had size, they had structure, but they produced no light and absorbed no light. They were detectable only through their gravitational effects on other matter. The smallest halos formed first. These contained perhaps 1 million times the mass of the Sun, concentrated in a region a few hundred light years across. The dark matter particles in these small halos moved in elliptical orbits around the halo center, crossing and recrossing, creating a diffuse spherical distribution. The density was highest at the center and declined gradually toward the edges. Larger halos took longer to form. A halo containing 1 billion times the mass of the Sun required more time to accumulate that much matter. The gravitational pull of such a large mass was strong, drawing matter from a larger region of space, but the distances were greater. Matter had to travel farther to reach the halo center. The formation timescale for large halos was tens of millions of years or more. The halos had profiles. The density as a function of distance from the center followed a particular pattern. Near the center, the density was high. Moving outward, the density declined, first gradually, then more steeply. At large distances from the center, the density approached the background density of the universe. The transition from halo to background was smooth, not sharp. There was no clear edge to a halo. The shape of halos was approximately spherical. Small deviations from perfect spheres existed. Some halos were slightly elongated. Some were slightly flattened. These departures from sphericity reflected the conditions under which the halo formed, the direction from which matter fell in, the influence of nearby structures. But the overall shape was roughly spherical, a consequence of gravity acting equally in all directions. The halos were not isolated. They existed within a larger gravitational field created by the distribution of matter throughout space. Nearby halos exerted gravitational pull on each other. Distant halos contributed to the large-scale gravitational field. Each halo felt the influence of all the other mass in the universe, weighted by distance. The nearest halos had the strongest influence. The most distant halos contributed almost nothing. The motion of halos reflected this gravitational field. halos moved through space, drawn toward regions of higher density. Small halos drifted toward larger halos. Halos and filaments moved along the filaments toward the nodes where the filaments intersected. The motion was slow, a few tens of kilometers per second in most cases, but over millions of years, this motion carried halos across significant distances. The environment shaped halo evolution. Halos in dense regions grew faster through mergers with other halos. Halos in sparse regions grew more slowly, accumulating matter mainly through the infall of diffuse gas rather than through mergers. The largest halos formed in the densest regions, where the most matter was available and where mergers were most frequent. The hydrogen began accumulating in the dark matter halos once the halos were sufficiently massive. The gravitational pull of a small halo was weak. It could not easily capture gas from the surrounding space. The gas had pressure, and pressure allowed the gas to resist compression. Only when a halo reached a certain mass threshold did its gravity become strong enough to overcome the gas pressure and pull hydrogen inward. The threshold mass depended on the gas temperature. Colder gas had lower pressure and could be captured by less massive halos. Warmer gas had higher pressure and required more massive halos. During the cosmic dark ages, the gas was very cold, so even relatively small halos could begin capturing hydrogen. Halos with masses of 1 million solar masses or more could accumulate some gas. Larger halos accumulated gas more efficiently. The gas fell into the halos from the surrounding space. It drifted inward along the gravitational gradient. As it approached the halo's center, it accelerated. The velocity increased as the gravitational pull grew stronger. Near the center, the gas might be moving at tens of kilometers per second. This was fast by the standards of the Dark Ages, though still slow compared to motions in later eras. The inflowing gas carried angular momentum. Angular momentum is conserved in the absence of external torques. As gas fell inward and the radius of its orbit decreased, the rotation speed had to increase to conserve angular momentum. The gas began to spin. It could not fall directly to the center. Instead, it settled into orbits around the center, forming a rotating distribution. The rotating gas flattened into a disk shape. Gas moving in different directions collided occasionally. The collisions caused the gas to lose energy. The loss of energy caused the orbits to shrink. Over time, the gas settled into a configuration where most of the motion was in the same direction, a disk rotating around the halo center. The disk was thick at this stage, not the thin disks that would form later, but it had a definite flattened structure. The disk continued to grow as more gas fell in. The infall was continuous. Gas from the surrounding space drifted inward, joined the rotating disk, added its mass to the growing structure. The disk became denser over time. The increase was gradual, accumulating over millions of years. The density in the disk's center might reach tens of thousands of atoms per cubic centimeter after 100 million years. This was still a very low density. The disk was diffuse, barely more substantial than the best vacuum achievable in a laboratory. But by the standards of the cosmic dark ages, it was a significant concentration. The density was hundreds or thousands of times higher than the average density of the universe. Structure was forming. Matter was gathering. The conditions were slowly approaching the point where further changes might occur. The temperature in the disk remained low. The gas had warmed slightly during infall due to compression, but the warming was modest. The temperature might be 30 to 50 degrees above absolute zero in the disk, compared to 10 to 20 degrees in the voids. The gas was still far too cold to ionize. It remained neutral. It remained dark. The disks did not emit light. The gas was too cold. The density was too low. No processes were occurring that could produce photons. The disks were invisible, like the dark matter halos that contained them. Structure was forming throughout the universe, but it was all dark structure, detectable only through gravitational effects. The universe at this stage contained millions of dark matter halos with rotating disks of neutral hydrogen. The halos ranged in mass from 1 million to 1 billion times the mass of the Sun. The disks ranged in size from a few hundred light years to a few thousand light years across. They were spread throughout space, separated by millions of light years, distributed along the filaments of the cosmic web. Each disk existed in isolation, unaware of the others. There was no communication between them. No light traveled from one to another. No material flowed between them. Each disk evolved independently, governed by the local conditions, the mass of its halo, the amount of gas available, the gravitational influence of nearby structures. The disks rotated slowly. The rotation period depended on the mass of the halo and the size of the disk. A disk in a massive halo might complete one rotation in 10 million years. A disk in a less massive halo might take 50 million years. The rotation was steady, neither accelerating nor decelerating, maintained by the balance between gravity pulling inward and the centrifugal effect of the rotation. The gas in the disks was in motion, but the motion was orderly. The gas moved in circular or slightly elliptical orbits. There was no turbulence, no chaotic swirling. The motion followed the gravitational field precisely. Each particle of gas moved along its orbit, maintaining its distance from the center, circling endlessly through the darkness. Collisions between atoms occurred more frequently in the disks than in the surrounding space. The density was higher, so atoms encountered each other more often. The collisions were still rare in absolute terms. An individual atom might collide with another atom once every few thousand years. But this was frequent compared to the voids, where collisions might occur once every few million years. The collisions did not change the large-scale structure. They shuffled energy and momentum among individual atoms, but did not affect the overall dynamics of the disk. The disk continued rotating. The gas continued falling in from outside. The density continued increasing gradually. The collisions were a minor detail, a microscopic process occurring within the larger flow. The hydrogen molecules began forming in the densest regions of some disks. Molecular hydrogen forms when two hydrogen atoms meet and bond together. The process requires a third particle to carry away the excess energy, otherwise the molecule immediately dissociates. In the densest regions, where collisions were most frequent, molecular hydrogen could form slowly. The amount of molecular hydrogen remains small. Perhaps 1 in 10,000 hydrogen atoms bonded into molecules. The rest remained atomic. But even this small fraction was significant. Molecular hydrogen can cool gas more efficiently than atomic hydrogen through the emission of infrared radiation. The presence of molecules allowed the gas to lose energy more quickly. The cooling was slow. The density was still low even in the disk centers. The molecules were rare. The emission was faint. But over millions of years, the cooling had an effect. The gas in the disk centers became slightly colder than the surrounding gas. The temperature might drop from 40 degrees to 30 degrees in regions where molecular hydrogen was present. The difference was modest but real. The colder gas compressed more easily. With lower temperature came lower pressure. Lower pressure meant less resistance to gravitational collapse. The regions where molecular hydrogen formed could compress to slightly higher densities than the surrounding gas. The density in these regions crept upward, reaching perhaps 100,000 atoms per cubic centimeter in the very densest spots. This was still extraordinarily diffuse, but the trend was clear. Gravity was winning, matter was gathering, density was increasing. The universe was changing, slowly but steadily, approaching conditions that would eventually allow new processes to begin. The universe continued in darkness. 100 million years had passed since recombination. The structures that had formed remained invisible. The dark matter halos were dark. The hydrogen disks were dark. The filaments connecting the structures were dark. No sources of light existed anywhere in the cosmos. The cosmic microwave background had cooled to approximately 3 degrees above absolute zero. The radiation had redshifted from microwaves into longer wavelengths, approaching the radio portion of the spectrum. The intensity had diminished as the photons spread across the expanding volume of space. The glow was faint, uniform, and carried little energy. The hydrogen gas in most regions had cooled to similar temperatures. In the voids, the temperature was perhaps 10 degrees above absolute zero. In the disks within halos, it was perhaps 30 to 50 degrees. The temperature differences reflected the local conditions, the degree of compression, the presence or absence of molecular hydrogen. But everywhere, the gas remained cold. Cold gas has very little thermal energy. The atoms move slowly. Their kinetic energy is minimal. They drift through space at velocities determined more by gravity and large-scale flows than by random thermal motion. The cold made the universe quiet in a thermal sense. There was little energy available to drive processes or cause changes. The darkness and cold together created a kind of stasis. The universe was evolving, but the evolution was slow. The structures were growing, but the growth was gradual. Density increased incrementally. Halos merged occasionally. Gas continued falling into the densest regions. But nothing happened quickly. Nothing changed dramatically. Time passed in a steady, unchanging rhythm. The waiting continued. The universe existed in this state, dark and cold, structured but inactive. The matter was arranged into halos and disks and filaments. The dark matter provided the gravitational framework. The hydrogen filled the gravitational wells. But nothing new was emerging. The universe had reached a kind of plateau, a long pause between the end of recombination and the beginning of whatever would come next. The pause was not truly static. Motion continued. Expansion continued. Gravity continued its work. But the changes were incremental. After 100 million years, the universe was larger, colder, and more structured than it had been after 50 million years. After 150 million years, it would be even more so. The trends continued without interruption, but the rate of change was slow. The universe was patient. There was no urgency. Physical processes operated at their own pace, determined by the laws governing gravity, expansion, and thermodynamics. The timescales involved were measured in millions of years. A million years was a short interval in the context of cosmic evolution. 10 million years was modest. 100 million years was substantial, but not exceptional. The densest regions within the hydrogen disks continued to evolve. Gravity pulled gas inward toward these density peaks. The gas compressed slowly. The density increased gradually. After 150 million years, some regions might reach densities of several 100,000 atoms per cubic centimeter. This was still diffuse, but it was approaching conditions where further changes might become possible. The molecular hydrogen fraction increased in these dense regions. With higher density came more frequent collisions. More collisions meant more opportunities for molecules to form. The fraction of hydrogen in molecular form might reach 1 in 1,000 in the densest spots, perhaps 1 in 100 in exceptional cases. The molecules continued to emit faint infrared radiation, cooling the gas. The cooling from molecular hydrogen emission was slow. The process removed energy gradually over millions of years. The temperature in the densest regions dropped from 40 degrees to perhaps 20 or 25 degrees. The cooling was not rapid. It did not cause sudden collapse. It simply allowed the gas to compress more easily by reducing the pressure that would otherwise resist further compression. The size of the dense regions was small. A typical dense core might be a few light years across. Some were smaller, perhaps 1 light year. Some were larger, perhaps 10 light years. These scales were tiny compared to the size of the halos themselves, which spanned hundreds or thousands of light years. The dense cores were small pockets of slightly higher density within the larger disk structure. The mass contained in these cores was modest. A core a few light years across, with a density of several 100,000 atoms per cubic centimeter, might contain a few hundred times the mass of the Sun. Some cores contained more mass, some contained less. The variation depended on local conditions, how much gas had accumulated, how efficiently the gas had cooled. The cores were not isolated. They existed within the rotating disks. The gas in the cores rotated along with the rest of the disk. The cores had angular momentum. They could not collapse directly inward to a point. The rotation prevented complete collapse, just as it prevented the entire disk from collapsing. The gas could compress along the rotation axis more easily than it could compress perpendicular to the rotation axis. The result was that the cores began to flatten. They were already part of a disk structure, but they flattened further. A core that started roughly spherical might evolve into an oblate shape, flattened along the axis of rotation. The degree of flattening depended on how rapidly the core was rotating. Faster rotation produced more flattening. Slower rotation allowed the core to remain more spherical. The cores continued to accrete gas from their surroundings. Gas in the surrounding disk drifted inward, drawn by the gravity of the core. The infall was slow. The gas spiraled inward gradually, taking thousands or millions of years to travel from the outer disk to the core. As the gas fell in, it added its mass to the core. The core grew slowly over time. The universe had now reached approximately 150 to 200 million years after recombination. The structures that had been forming were now well established. Dark matter halos filled space along the filaments of the cosmic web. Hydrogen disks rotated within the halos. Dense cores had formed in some of the disks. The hierarchy of structure extended from the cosmic web at the largest scales down to cores a few light years across at the smallest scales. Nothing had changed the darkness. The universe remained dark throughout this entire period. No light had been created except the fading cosmic microwave background. The structures were invisible. The cores were invisible. The entire universe existed in a state of darkness that had persisted for hundreds of millions of years. The conditions in the densest cores were approaching the thresholds where new processes might begin. The density was high enough that gravity was becoming significant on small scales. The temperature was low enough that the gas pressure was minimal. The mass was sufficient that further collapse might lead to new configurations of matter. But none of this had happened yet. The universe was waiting. Not waiting in any conscious sense, but existing in a state where conditions were approaching critical values but had not yet reached them. The gas continued to cool. The density continued to increase. The cores continued to accrete mass. The processes that would eventually lead to change were ongoing, but the change itself had not yet occurred. Timescales remained long. The processes operating in the cores took millions of years. The cooling took millions of years. The accretion took millions of years. Everything happened slowly. There were no sudden transitions, no rapid collapses, no dramatic events, just the slow, patient accumulation of matter and the gradual evolution of physical conditions. The cold persisted. The gas in the cores was perhaps 20 degrees above absolute zero. The gas in the disks was perhaps 30 to 40 degrees. The gas in the voids was perhaps 10 degrees. The cosmic microwave background was approximately 3 degrees. Everything was cold. The universe had reached nearly its coldest state, the lowest temperatures it would experience before new energy sources emerged. The silence persisted. No sounds propagated through the sparse gas. No disturbances created waves. No shocks traveled through space. The universe was as quiet as it had been for the entire Dark Age. The motion was smooth and continuous. The flows were laminar. The gas drifted and spiraled without turbulence, following the gravitational field in orderly patterns. The waiting continued without any sense of anticipation. The universe did not know that conditions were approaching thresholds. Physical processes simply operated according to their nature. Gravity pulled matter together. Expansion carried space outward. Cooling reduced temperatures. Accretion added mass to dense regions. These processes continued in the darkness, patient and persistent, following the logic of physics through the long night. The darkness remained complete. The structures remained invisible. The cores remained dark. The hydrogen remained neutral. The universe existed in this state, dark and cold and structured, evolving slowly towards some future state that had not yet been reached. The Dark Ages continued. The waiting continued. Time passed through the silent cosmos, measured only by the slow ticking of physical processes operating on timescales of millions of years. 200 million years had passed since recombination. The universe had been dark for all of that time. The structures had grown slowly through the accumulation of matter and the patient work of gravity. The dense cores within the hydrogen disks had continued to evolve, compressing gradually, cooling slowly, accreting mass from their surroundings. The delay in star formation was not a failure of any process. It was simply the time required for conditions to develop. Stars require particular conditions to form. The gas must be dense enough that gravity can overcome all forms of resistance. The gas must be cool enough that pressure does not prevent collapse. The gas must accumulate enough mass in a small enough volume that the gravitational pull becomes overwhelming. These conditions took time to establish. The density had to increase through the gradual infall of gas. The temperature had to decrease through the slow emission of radiation by molecules. The mass had to accumulate through the patient gathering of matter from larger and larger regions of space. None of these processes could be rushed. Each operated at its own natural pace. The universe provided no mechanism for acceleration. There were no feedback processes that could speed up the evolution. No energy sources existed to heat gas and drive rapid changes. No radiation pressure existed to compress gas quickly. Only gravity and cooling operated, and both worked slowly when the density was low and the temperature was already near the minimum possible values. The dense cores in some regions had reached masses of several hundred times the mass of the Sun. The density in the core centers had reached perhaps 1 million atoms per cubic centimeter. The temperature had dropped to approximately 15 to 20 degrees above absolute zero. These values represented substantial evolution from earlier conditions, but they were still far from the conditions found in stars. Stars have densities measured in grams per cubic centimeter, not atoms per cubic centimeter. 1 gram per cubic centimeter corresponds to roughly 10 to the 24th atoms per cubic centimeter. The densest cores during the Dark Ages were still 20 orders of magnitude less dense than stellar material. The gap was vast. Bridging that gap would require continued compression over long time scales. Stars have temperatures measured in thousands or millions of degrees. The cores during the Dark Ages were 20 degrees. The gap in temperature was even larger than the gap in density. Temperature would eventually increase through compression, as gravitational potential energy converted to thermal energy during collapse. But the collapse had to proceed far before temperatures would rise significantly. The delay reflected these enormous gaps in physical conditions. Moving from atoms per cubic centimeter to grams per cubic centimeter required compression by a factor of 10 to the 24th. Moving from 20 degrees to thousands of degrees required heating by a factor of 100 or more. These changes could not happen quickly when the starting conditions were so extreme in the opposite direction. The cores continued their slow evolution. Gas fell inward under gravity. The density increased incrementally. After 250 million years, some cores might reach densities of several million atoms per cubic centimeter. After 300 million years, perhaps 10 million atoms per cubic centimeter. The progression was steady, but the pace remained slow. The molecular hydrogen fraction continued to increase with density. More collisions meant more molecule formation. The fraction might reach a few percent in the densest cores by 300 million years. The molecules continued to radiate away energy, cooling the gas. The temperature in the cores remained between 15 and 25 degrees in most cases. The cooling from molecular hydrogen had limits. The molecules could only cool the gas to approximately 10 degrees above absolute zero under the conditions that existed. Below that temperature, the energy levels within the molecules were too far apart to be excited by the available thermal energy. The cooling became inefficient. The gas temperature stabilized at this minimum value. Some cores reached this temperature floor. The gas in these cores was as cold as it could become through molecular cooling. Further cooling would require other processes, other mechanisms to remove energy. No such mechanisms existed during the Dark Ages. The gas remained at 10 to 15 degrees, unable to cool further, but still far too warm to be called anything but cold. The pressure in the cores remained low despite the increasing density. Pressure depends on both density and temperature. The density was increasing, which increased pressure, but the temperature was decreasing, which reduced pressure. The two effects partially offset each other. The net result was that pressure increased slowly, much more slowly than density increased. Low pressure meant that gravity could continue to compress the gas. If pressure had been high, it would have resisted further collapse. The gas would have reached an equilibrium where pressure balanced gravity and compression would have stopped. But with low pressure, no such equilibrium was reached. Gravity continued to dominate. The compression continued without being halted by pressure support. The cores were still far from the conditions needed for star formation, but they were moving in that direction. The evolution was slow, but it was happening. Each million years brought slightly higher density, slightly more molecules, slightly more mass. The cores were evolving towards some future state, though that state remained distant. The universe during this period was in a peculiar condition. It contained structure. It contained concentrations of matter. It contained the precursors to what would eventually become galaxies, but it remained inactive. The structures existed passively, shaped by gravity, cooled by radiation, but not generating any new phenomena. The universe was structured, but dormant. 300 million years after recombination, the universe remained dark. Some estimates suggest the first stars might have formed around this time. Other estimates suggest it took longer, perhaps 400 million years, perhaps even longer in some regions. The exact timing depended on local conditions that varied from place to place. The formation of the first stars would eventually occur when the densest cores compressed sufficiently. The compression would continue until the density became high enough that the gas could no longer be considered transparent. The atoms would begin to interact more frequently. The energy released by compression would begin to heat the gas significantly. As the gas heated, new processes would become possible. At higher temperatures, hydrogen atoms could collide with sufficient energy to excite the electrons into higher energy states. The electrons would then drop back down, emitting photons. The gas would begin to glow, first in infrared wavelengths, then in visible wavelengths as the temperature increased further. At even higher temperatures and densities, nuclear fusion would begin. Hydrogen nuclei would collide with enough energy to overcome their electrical repulsion and fuse together, forming helium. The fusion would release energy, generating heat and light. A star would ignite. The darkness would begin to end. But this had not happened yet during the time period this story covers. The cosmic dark ages were still ongoing. The cores were still cold. The density was still too low. The conditions were still below the thresholds required for these processes to begin. The universe continued in its state of darkness and cold. The waiting during this period was not empty. Evolution was occurring. Structures were growing. Conditions were changing. But the changes were incremental. Nothing dramatic was happening. The universe existed in a prolonged intermediate state between the simple uniformity of the early universe and the complex, luminous structures that would eventually emerge. The dark matter halos continued to merge and grow. Small halos combined into larger ones. The largest halos by 300 million years might contain several billion times the mass of the Sun. These were the ancestors of what would become large galaxies, but they were still dark. No stars had formed within them. They contained only dark matter and cold, neutral hydrogen. The cosmic web structure was fully developed by this time. The filaments and walls and voids were clearly defined. The density contrast between the densest regions and the emptiest regions had grown substantially. The overdense regions might be 10 times denser than average. The voids might be 10 times less dense than average. The universe had developed a clear, large-scale structure. The hydrogen in the voids remained especially diffuse. The density there was perhaps 1 atom per 10 cubic meters. The temperature was approximately 10 degrees above absolute zero. The voids were emptier and colder than any other region of space. They were expanding faster than the rest of the universe, driven away from the overdense regions by the gravitational pull of those denser areas. The hydrogen in the filaments was flowing steadily toward the nodes where the filaments intersected. The flow was coherent and organized. Gas traveled along the filaments at velocities of perhaps 20 to 30 kilometers per second, following the gravitational gradient. Over tens of millions of years, this flow transported vast amounts of gas from the filaments into the halos at the nodes. The universe continued in this state, dark, cold, structured but inactive. The processes that would eventually lead to the first stars were ongoing in the densest cores. The compression continued, the density increased, the mass accumulated, but the critical thresholds had not yet been reached. The Dark Ages continued through their third 100th million year, patient and persistent, waiting for conditions to reach the point where light could finally return to the cosmos. The cosmic Dark Ages represented a unique period in the history of the universe. It was a time unlike what came before and unlike what would come after. Before the Dark Ages, the universe was hot and dense, filled with plasma and radiation. After the Dark Ages, the universe would be illuminated by stars and galaxies, active and luminous. But during the Dark Ages, the universe was cold, dark, and quiet. The duration of this period was substantial. From recombination at 380,000 years to the formation of the first stars at perhaps 300 to 400 million years, the Dark Ages lasted hundreds of millions of years. This was longer than many other cosmic epochs. It was a significant fraction of the universe's early history. During this entire period, matter existed but did not shine. Structure formed but remained invisible. Gravity shaped the distribution of matter into hierarchies of halos and filaments and voids. The hydrogen accumulated in the gravitational wells created by dark matter. The gas cooled and compressed slowly. All of this happened in darkness. The darkness was total in the wavelengths that human eyes can perceive. No visible light existed except the fading glow of the cosmic microwave background, which had redshifted far beyond the visible spectrum. An observer with human eyes, had such an observer existed, would have seen nothing. Perfect darkness in every direction. No stars, no galaxies, no glowing nebulae, just blackness. The cold was nearly absolute. Temperatures approached the lowest values that matter would ever reach, 10 to 20 degrees above absolute zero in most regions, perhaps 50 degrees in the densest cores. These temperatures were far below anything experienced in later cosmic history. Once stars formed, they would heat their surroundings. The universe would never again be as cold as it was during the Dark Ages. The silence was complete. No sounds propagated through the sparse gas. No shock waves traveled through space. No acoustic oscillations disturbed the medium. The universe was quiet in a profound sense. Motion occurred, but it was smooth and laminar. Flows happened, but they were gentle and continuous. Nothing created disturbances that could be called sound. The patience of the universe during this period is difficult to comprehend from a human perspective. Millions of years passed with only gradual changes. Processes unfolded over timescales that dwarf human experience. A million years is nearly incomprehensible to human minds. 10 million years is beyond intuitive understanding. Yet these were the timescales on which cosmic evolution operated during the Dark Ages. The structures that formed during the Dark Ages established the framework for everything that followed. The dark matter halos that formed became the gravitational wells in which galaxies would eventually form. The filaments and voids that developed became the large-scale structure that persists today. The cores that accumulated gas became the sites where the first stars would ignite. The distribution of structure was not uniform. Some regions had higher densities and formed more halos. Other regions were emptier and formed fewer structures. This variation meant that star formation would not begin everywhere simultaneously. The first stars would form in the densest regions, where conditions reached critical thresholds first. Other regions would remain dark for longer. The variation created a gradual transition from the Dark Ages to the era of the first stars. The darkness did not end suddenly everywhere at once. It ended first in isolated locations, then spread gradually as more stars formed. Regions near the first stars would be illuminated first. Distant regions would remain dark longer. The transition occurred over tens or hundreds of millions of years. The first stars themselves would be different from later stars. They would form from gas that contained only hydrogen and helium, no heavier elements. This would affect their properties. They would be massive, much more massive than typical stars today. They would be hot and bright. They would burn their fuel quickly and live short lives. But they would produce light, and that light would begin to change the universe. The light from the first stars would ionize the surrounding hydrogen. Neutral hydrogen absorbs certain wavelengths of ultraviolet light, and the energetic photons from hot stars would strip electrons from hydrogen atoms. The gas around the first stars would transition from neutral to ionized. Bubbles of ionized gas would form around each star, growing slowly as the radiation spread outward. Eventually, these bubbles would overlap. As more stars formed and more bubbles grew, they would merge together. The universe would transition from mostly neutral to mostly ionized. This process is called reionization. It would take hundreds of millions of years to complete, but it would mark the end of the Dark Ages and the beginning of a new era. The cosmic Dark Ages would end, not with a sudden flash, but with a gradual brightening. First one star, then another, then more. Slowly, over vast spans of time, light would return to the cosmos. The darkness that had persisted for hundreds of millions of years would give way to illumination. The cold, neutral hydrogen would give way to warm, ionized gas. The quiet universe would become active. But during the Dark Ages themselves, before any of this happened, the universe remained in its state of darkness and cold. The structures continued to evolve slowly. The cores continued to compress gradually. The conditions continued to approach the thresholds where stars could form. The universe waited patiently for the moment when the first light would appear. The cosmic Dark Ages were a time of potential. Everything that would later shine was present but dormant. The matter was there. The structures were forming. The conditions were evolving toward the point where stars could ignite, but the ignition had not yet occurred. The potential existed, but had not yet been realized. This period reminds us that the universe operates on timescales far beyond human experience. Hundreds of millions of years passed while conditions slowly developed. There was no impatience, no urgency, just the steady operation of physical processes following the laws of nature. Gravity pulled matter together. Expansion carried space outward. Cooling reduced temperatures. Each process operated at its own natural pace. The darkness was not emptiness. The universe during the Dark Ages was filled with matter, filled with structure, filled with activity at the level of atoms drifting and gas flowing. But it was dark because no processes were occurring that could produce light. The matter existed, the motion occurred, the evolution proceeded, but all of it happened invisibly. The cold was not stillness. The atoms were moving, though slowly. The gas was flowing, though gently. The structures were rotating, though gradually. Motion continued throughout the Dark Ages, but the motion was at low velocity and low energy. The thermal motion was minimal. The kinetic energy was small. Everything moved in a slow, cold dance through the darkness. The silence was not absence. The universe was full of matter, full of gravitational fields, full of quantum processes at the smallest scales. But it was silent because no disturbances created waves in the medium. No compressions and rarefactions propagated through the gas. No vibrations traveled through space. The universe was full, but quiet. The waiting was not conscious. The universe did not know it was waiting. It simply existed in a particular state, evolving according to physical laws, changing slowly as time passed. The conditions that would eventually allow stars to form were approaching, but there was no awareness of this, no anticipation, just the blind operation of gravity and thermodynamics moving the universe through a long, dark, cold phase. The Dark Ages eventually ended. The first stars eventually formed. Light eventually returned to the universe. But for hundreds of millions of years, the universe existed in darkness, cold, quiet, structured but invisible, evolving slowly towards something new, patient in a way that only the universe can be patient, operating on timescales measured in hundreds of millions of years, following the logic of physics through the long cosmic night. The story of the Dark Ages is a story about time, about patience, about slow change accumulating over vast durations, about the universe existing in a state that seems static on human timescales, but is actually evolving steadily on cosmic timescales. It is a reminder that the universe operates according to its own rhythms, its own timescales, independent of human perception or human experience. The darkness was long, the cold was deep, the silence was profound, but the universe continued. Matter drifted through space, structures grew slowly, conditions evolved gradually, and eventually, though it took hundreds of millions of years, the conditions reached the point where stars could form. The darkness began to end, light began to return. But before that moment, for a very long time, the universe was dark. For a very long time, nothing in the universe was illuminated.